I want to get into the talk now, and there's two things that I want you to take away from this. Would be, I view the times that we're in now as being really uncharted waters. There's more unknown and uncertainty than there's ever been in our industry. For engineers, though, I think that gives us all a chance to be our most creative, because there are things that are going to have to be different to continue the pace that we've been on in the past. And therefore, I consider this to be the most exciting time that there ever has been in the semiconductor industry. And I say that having been involved in some very dramatic change. If you subtract 40 from this year, you'll think about the time that cell phones came into play. I started designing RF and analog custom IC circuits for communications for land mobile radios long before basically cell phones were a gleam in anyone's eye. So I've been a part of two dramatically growing industries, that the semiconductor industry and the communications industry, throughout my career, and I feel very lucky and fortunate to have done that. But I think today is even more exciting than those days have been, because of the challenges that are facing us and the opportunity to apply our creativity. So, point one is most exciting time in the history of the industry. Point two is that it's going to require investment in research. Companies have got to start to realize that the future is not so guaranteed as it used to be, where we were migrating down one technology node to the next. For sure, there's been substantial roadblocks along the way, but we have gotten through those hurdles. The roadblocks we're facing today are significantly more challenging than they've ever been. So we need to, as an industry, double down on the research, and there's no better place, in my mind for sure, than to do that through SRC, because we take a consortial approach to this, which allows you to leverage your money, and I'll speak a little bit more about that on other slides. So point two is we need to double down in our research investment across the semiconductor space, definitely including test, and I'd like to see you do that through SRC. So those are the two things I want you to take away from here today. So this is the outline of my talk. I'm going to talk about the industry challenges, both from a business perspective and a technical perspective, as well as the opportunities as I see them. Give some specific examples of some real challenges that are further out in time, but if we don't do something, we're in big trouble. Talk about some of the SRC-sponsored research as it's applied to some of this problem set, and give you at the end a couple of slides on what SRC is about and summarize. So just to prove my point about the importance of SRC in this space, I captured the three keynote speakers here, and the first one being Wally Rines on Tuesday, who's been a board member for over 20 years at SRC, and he heads our research committee, so he's driving where we should invest money for research. Being in the segment of the market he's in, that's near and dear to a lot of you. Rob came yesterday, and he has been a long-time funded PI of SRC. He ran a center at one point in time, and that amounted to over $45 million of investment in university research funding through the center that Rob ran. And personally, we have funded him and his graduate students over $2 million throughout his career. And then today, you're stuck with me. Conclusion is, if you want to be a keynote speaker in the future, join SRC. Okay, so look at where we stand from a industry growth perspective. Last year was a down year, slightly down, slightly negative. This year, this past quarter, third quarter, has been the highest sales volume in any quarter in the semiconductor industry history. Fourth quarter is supposed to be up compared to fourth quarter last year, yet those combined effects may not cause this year to be a growth year over last year. May or may not. It's a don't know. So if you take the pessimistic assumption and say it's going to be a declining year, it'll be a small decline. That will be 2 years in a row we've had a decline in the market, which is only the second time in the history of the semiconductor industry that will have occurred. The only other time was during the massive global economy disaster of 08 and 09. So we are in a situation from a growth perspective that if you look at it today or with a glass half full, it doesn't look particularly good. However, I have a lot of optimism for the future, and I think there's these two big trends out here. There's an insatiable demand for data, and that data is going to be collected on the things at the edge of the Internet of Things. So there's two market areas, big data and IoT, that I think will be clear market drivers and demands for growth in our industry. Besides being maybe kind of cool or something like that, I think another reason to believe in that kind of argument is they do impact a lot of the societal goals that are important, such as taking care of the aging population, the baby boomer phenomenon, of which I'm one of those. The first of those hit age 65, I think it was January 1, 2012, recently. There's a similar group of people in Western Europe. Those two groups represent something like 75% of the disposable income of the two continents. So they're very wealthy and very well poised to fund or purchase gadgets, if you will, that will improve their quality of life as they go forward, rather than being shoveled into a nursing home or someplace like that for assisted living. So that's one population that's looking forward to advances in the medical health perspective, as well as just the general health well-being. There's huge opportunities, and I'll talk about one of them that we're starting at SRC in that space, which is a wholly different way of approaching it. Autonomous transportation. It's from the auto manufacturer's perspective, it really addresses one of their major goals of zero fatalities that they're trying to achieve, but it also frees up a lot of time for us. So I think there's plenty of opportunity from a market perspective for the continued growth of our industry. A couple of specific examples, starting in the upper left-hand corner, high-performance computing, which is kind of a niche space. Even that niche space, and these are all 2020 numbers, is expected to be a $36 billion industry growing at over a 5% CAGR. Mobile health and ADAS for the automotive industry, $60 billion industries growing at 33% and 23% respectively. And then lastly, the Internet of Things, which there's wild numbers all over the place. This particular article says 1.7 trillion in 2020, of which 50 billion is expected to be semiconductor-related devices, with a 17% compounded annual growth rate. So big markets and rapidly growing markets that demand advances in technology. So what are some of the challenges that we're facing? I think we finally all come to grips with the fact that Moore's law is slowing from the perspective of a dimensional scaling aspect. An atom's diameter is roughly a quarter of a nanometer, so there is a lower bound on how far you can go that way. But Moore's law was really written as an economic, wasn't a law at the time, but economic law, and that the cost per transistor would go down every couple of years by a factor of 2-ish. So the question is, how do we sustain that economic law going forward in a different way than simply dimensional scaling, because that won't work. The devices that are scaling are becoming more and more stochastic or statistical in nature. This breaks the fundamental principle of IC design, at least as I knew it when I started, which was you put down two devices side by side, and for all intents and purposes, they are identical. Today, at these smaller geometry nodes, they're not even looking like cousins. So how do you not just deal with that stochastic nature of those devices, how do you exploit it to your advantage? It's something that we're considering through research, and I'll talk about that. And there's the demand for more and more sensors and developing cost-effective and power-efficient sensors. as well as how do I partition my systems given the fact that moving to these advanced nodes is costly in terms of development cost, and I'm not seeing the advantage from a transistor cost that I had in the past. So it speaks to other ways of integrating. But the two key drivers to me from a technical perspective are these last two, power consumption and security. We are power constrained with what we can do. On the server end, we build chips as big as we can, with as many cores as we can put on them, that we can get the heat out of the device. We aren't limited by the dimensions of the chips, we're limited by the power they consume. On the edge, on the other hand, it's how long will that device last in the field? How sustainable can it be? How long? What kind of energy source do I have there? So what it can do is limited by the power it has available to it. The security side of this is the threat side in a way, in that as we build out this Internet of Things, we are providing more and more access points. So we're increasing the attack range, if you will, by adding on these things which can't be clearly as secure as the at the server end, and continued hacks through those systems, bringing people to their knees, will slow down the growth of the market more than anything else will. You can see the example there and the impact it had on Target when they had their security hack. So from a business perspective, it's very dramatic if that situation occurs to your business. So security has now become something that people are actually willing to pay for, and it's going to be fundamental to every design that we do. There is an element of test in security for sure, and that is how do you test to ensure that a device does only what it's supposed to do and not some other things that some malicious act may have taken place in between. So there's a huge opportunity in here for test type people to make a big difference. So continuing on a little bit with the opportunities, package integration's always been on the table, but rarely implemented, because when you looked at the cost savings that you got compared to that in silicon integration, it really never would work out. But today, there's real opportunity for that in the form of fan-out type of packages or 3D systems, and I'll talk a little bit about that. We have been racing from node to node to node because the process technologists have been able to do that. Because of that, I think we've left a lot on the table from an architectural exploration space. And I think there's a lot of room there excuse me, to take advantage of for some period of time. In the compute space, it's looking at architectures different from von Neumann, like normorphic computing. Maybe said another way is building co-processors or accelerators to do specific functions very efficiently compared to running them on a general purpose compute type engine. There's big opportunities for developing new algorithms that can be done more efficiently, even with the compute resources that we have. In my last role inside of Freescale, this is an area that we were working on and saw tremendous gains by optimizing the algorithms, which again, the time hasn't permitted so much in the past. And then some applications like video or pictures, if you're missing a pixel, it really doesn't matter. Your eye integrates right through that. So how do I exploit approximation and randomness to my advantage, at least in some application space, is another place to take advantage of the situation. If we can't add performance, not saying that we can't, if we can't lower costs, not saying we can't, we can add features to make the product that we provide more valuable. And first and foremost to me is in the security space, which I talked a little about already. Secondly is in human-computer interaction. From my point of view, Steve Jobs is the king of HCI and a genius in that space. But I think he's been dead for about 3 years. And if you'll notice, Apple hasn't come out with any really ingenious HCI device since. And so I think there's opportunity here for some new research for someone to become the next Steve Jobs, if you will. And then lastly, in the EDA space, again, because In part, we've been racing ahead, in part because the EDA providers have to support the smallest geometry nodes today, and many people are designing on the backwards technology, if you will. Exploiting those tools in the bigger geometry nodes may provide opportunities to actually just reduce your power, your die size, or improve your performance by optimizing your design, because either you have more time or you have better tools, or a combination of both, as well as the EDA guys may provide some updates. So if I were to summarize that from a technology perspective, for the future, we need to invent and build technologies that enable us to handle this simultaneous explosion in collecting at the edge, communicating through the gateways and up to the cloud, moving, storing, analyzing that data in a way that we can convert it from just raw data to information, and do that at speeds and volumes and with efficiencies orders of magnitude better than we can do today. This is I think the single way I would express the technical challenges of the future and the opportunity to grow the market. And as I said before, I believe it requires us to double down and invest more in research to find ways to do this. I read something earlier this week that said that data is the new oil. And I thought about that and said, yeah, that's kind of right, but I thought about it a little bit more. I think it's more like the new gold. And if you go back to the panhandler days you would scoop up a pile of stuff and you would sift through it to find the nuggets. That's what we're trying to do with getting the information out of this pile of stuff that we're collecting. We're trying to figure out what are the nuggets in there that we can actually use and take action on. So I think data is the new gold of the 40s or 20s, if you will. That'd be the 1920s and 1940s. Okay, so let me get into a couple of specific cases here and show you the kind of problems that we're up against as we see it from some work that we've done at SRC and working with Hilbert and Lopez. That chart on the lower right, the red dots are the rate of growth of storage, total storage worldwide. If you extrapolate that out, you get to a need in 2040, roughly 25 years now, of 7 times 28 bits of storage requirement. Using a more conservative track based on a shallower slope that we've seen over the last 20 years or so, and assuming it stays on that shallower slope, says it will need 3 times 10 to the 24th bits in 2040. If you start calculating back from that using the size of the memory storage element today, flash, as it would move down in size as a function of geometry or node that you're at, and determine how much silicon you need to provide 10 to the 24th bits of storage, it turns out it's 10 to the 9th kilograms of silicon, of which there's only 10 to the 7th or 10 to the 8th kilograms available today. So that says just for storage alone, we won't even have enough silicon to produce to support the storage need if you extrapolate out that far. So that suggests that we need to do it a different way. If you take now and look at the communication capacity and extrapolate out to the same time frame, the total capacity capability will be on the order of 2 times 10 to the 23rd bits per year. If you say that going back to that, I need to store that 3 times 10 to the 24th bits and figure out how long that is, it takes 15 years to store all the data through the communication capacity that we will have in that time. So that's problem number 2. This chart has a couple of curves of showing energy consumption, normalized energy consumption for computing types of applications. Today, we're at about 10 to the minus 14th joules per bit, the red line. If you extrapolate that out over time, you would expect to, prior to 2040, exceed the total world energy production just for the compute type of application. And that world energy production is growing. It's a little hard to see on that graph, but it's at a very slow pace. So that's another problem. We can do things in the compute space, we think, of If you take the idea of these vertical nanowire devices, you can electrostatically couple information between nearby gates if you can lay them out appropriately like that, and if you have large fan-out, that's advantageous. You can look at the I/O, and you can do a couple of things there where you try to reduce the data that you transfer through the I/O by transferring information as opposed to data, and then perhaps doing 3D stacking where the coupling and capacitive loading is a lot lower, and you can do other things like do in-memory computing so that you're not moving data back and forth between the memory and the computational function. If you do all of those things, we estimate that's 10 to the minus 17th joules per bit, and that takes you out beyond 2035 beyond 2040, about another decade beyond where the cross point there is before you run into a problem. But the point here is those are three fundamental problems that are staring us in the face that, yeah, they're 25 years away, but if you don't start working on those kind of fundamental issues soon, you will never, ever solve them if you wait to say it's staring me in the face, what do I do? So as a result of that, we SRC, along with NSF and SIA, held a workshop last year and produced a report based on what should we do to try to address those kinds of problems called Rebooting the IT Revolution. You can Google it and read it if you like. It broke down into these 8 vectors of areas for research. 3 of them are compute-related: efficient sensing at the edge and computing, insight computing, converting the data to information, intelligent storage, this data storage problem I just spoke about, along with real-time communication. So how do I communicate from the edge to the gateway to the cloud, or from one car to the next, with real-time constraints? The cyber-physical space is speaking to this human-computer interaction problem. How do I do that? How am I going to do that different? I mean, one example of today is augmented reality kinds of things, but how do I do that different going forward? And then if I can build a solution, if you will, once, what do I need to do to make it manufacturable, and what are the next generation manufacturing needs to support that, along with, it would be nice if there was some way to have an IoT test platform, and this to me from the communication space is more like interoperability, testing between devices, but have that available so that we can start coming together on a set of components that everyone can use. This has all been refined since that time, and a research agenda working with DARPA has been put in place, a $40 million per year, 5-year program, so a $200 million research program called JUMP, Joint University Microelectronics Program, and for which there will be a research announcement tomorrow for any of the PIs in here that want to take a look at that. It'll be on the SRC website and presumably on the DARPA website. So this is next generation research opportunity funding. Besides the topics, we think there needs to be a different approach. This needs to be done in a co-optimized way across the design hierarchy stack, kind of cartoonly shown on this chart to be from materials up to applications. And similarly, it requires inner science research. The interesting problems occur kind of at the boundaries of where one guy's field ends and another guy's field starts, if you will. And so like in the case of algorithms, it's maybe between the math group and the computer scientists. How do I take a pure mathematical thing and implement it on a computer? With the materials and the device guys, given a device need, what materials can I choose to support that kind of need? So these interactions between experts in these different fields are going to be fundamentally important to solve the problems that lie in front of us, operating in distinct layers and passing things from one to the other like we typically have largely in the past, we don't believe will work. So let me jump into some of the research that we are funding at SRC. This is one of our center programs. It's called SONIC. What they are doing is taking a top-down approach, looking at the architecture. Can I, through my architecture, relax the requirements on the devices and or use the crummy devices that are coming out in a way such that the effort is on design as opposed on to building a better device. And so they're looking at stochastic processing via two methods. One is a brain-inspired approach, and the other is through a Shannon-inspired. Shannon is the father of communication and information theory, and his concepts are used every day in the cell phone that you've got, where if you did not take advantage of the learnings from Shannon, the link margin is so poor you would never ever receive a phone call. It has to be corrected. What's transmitted has to be corrected on the receiving end. And so they're doing this inside the chip, and I'll show you in a minute, maybe a little more. So brain-inspired. Why brain-inspired? Well, the brain is composed of a bunch of unreliable and noisy components, yet generally provides amazing performance in spite of this noisy kind of environment, time after time after time, and gives you the same answer under the same conditions. It's adaptive, so that it's continually learning. Machine learning is a big area of interest now, so using the brain as a model is a good starting place. One real advantage it has is it's got a seamless interface into the real world, which we always have to convert from the digital world to the analog and electronics. And then finally, it's got an extraordinarily high computational power to DC power consumption ratio. So we'll see that on this chart. If you take the same volumetric size of a silicon cell and an electronic cell and compare the power consumed for a task, it's 6 orders of magnitude lower power for the biology cell and the silicon cell. And if you look at how long it takes to compute, it's 2 orders of magnitude faster to compute for the biologically based cell. So combined, that's a 10 to the 8 order of magnitude, 8 orders of magnitude improvement in using the brain over using electronics as we kind of know them. We'll never be able to capture that entire 8 orders of magnitude, but there's a lot of waste that you can still take on and have tremendous improvement in the power consumption required. And so if you think back to that chart about energy and draw those, we were looking at a 10 to the minus 14th to a 10 to the minus 17th, that's 3 orders of magnitude. Drop that another 5-ish orders of magnitude. We just provided some room for quite a bit of time. On the Shannon-inspired side, it's in communication systems, you will build on the receiver something like a maximum likelihood sequence estimator, which will estimate the channel and for the incoming data then produce what was actually, convert that to actually what was transmitted with a maximum likelihood of probability. Those kind of concepts then are being applied to these silicon systems that are made up of these stochastic elements, which are unreliable components, and they're building reliable results out of them. Fundamentally, the same thing the brain is doing, a little bit different way. They're simultaneously really going after the power problem. So this is an architecture problem using poor devices and restricting the requirements on the device guy, and at the same time going after other ways of reducing power, which is built around this idea of data movement, as we all know, is the crux of power consumption in a compute system. We're constantly moving data, which adds no value to the output, but has to be done in order to manipulate the computational unit. So if we can not move as much data, we can reduce our power consumption dramatically. So they're looking at a traditional system here, and the front end of that, they are doing things like I've talked about, where they're doing in-memory computing, in-sensing computing, converting the data to information, and then passing the information along, which can produce dramatic improvements in the power consumption. But in their case, they are embracing the stochasticity of the system and doing this in a way to convert that data into information. Since Wally was here on Tuesday, you may have already seen these charts. I stole them from Wally. Wally has really good charts, as you probably already know. But they speak to the cybersecurity space. And there's Rod Beckstrom, who is the former director of the National Cybersecurity Center. Law associated with him now is that anything attached to the network can be hacked. Everything's being attached to the network, therefore everything is being hacked. I mean, kind of nothing could be further from the truth. And as we provide more and more entry points, it's more and more opportunities for hackers to try to take advantage of the system. So this chart shows the impact of a hack, and at the bottom it shows that if you attack at the hardware level, the impact of that's 1 billion times higher than attacking back at the top level at the user level. Yet, if you look at the funding that's going into research over these in the space, there's only 11% of it that goes into that physical hardware kind of layer. So this is pretty much in a sweet spot for SRC, hardware security. And one of the experts in hardware security sitting over here, Mark Taranapur, and I'm going to show an example of some of his work in here in a minute. So this is, and he's funded by SRC, obviously. At 2 universities, UConn and Florida, he's been funded. So we have taken on a program in this space, working jointly with NSF, and have funded $10 million of research so far, adding to that $1 million of research every year, minimally. In the areas of designing for security, so how do I design for test, how do I design for security? Verification of those security properties, so testing of them, so this is a space near and dear to your heart a little bit. Attack awareness, if I'm attacked, can I realize that and shut down? And then one area that's really of concern, particularly to the government, is counterfeit detection. I'll show a couple of examples on that, where we're moving the focus towards these edge devices because they're the ones that can be exploited the easiest. So here we go. Here's a couple examples. Mark's work at Florida, where he's taking a look at utilizing traditional memory elements in the form of SRAM or DRAM or flash, taking advantage of knowing that there's a sensitivity to aging of the SRAM bits, if you will, and exploiting that to determine if a device has been previously used and is being recirculated through a sale into the system, into the defense system, if you will, by having the knowledge now that device has actually been up and running and been used for some period of time, and therefore it's no longer a brand new device coming off the line as it's being advertised, if you will. Ken Mai at CMU, he's doing something maybe a little more just straightforward, and that is building a chip odometer, which is just recording events like how long has this part been in existence. One of the more interesting ones is, has there been some sort of extraordinary stress on the device that would be uncommon, and storing that information behind a hardware root of trust so it can be examined by the appropriate people to ensure that device truly is real and is not a counterfeit device. So I talked about what's going on in the sonic area on the architecture side, and my background is more in the circuits architecture side of things, and I see a lot of opportunity there for sure to continue making better devices that'll have value in the marketplace, and I'll say for some time. And I'll give you an example in the communications world is in the early 80s, at every vehicle or technology conference in those days, the talk of the town, if you will, was all about this new modulation format that was being invented called OFDM, orthogonal frequency domain modulation, which is exactly what's used in the Wi-Fi devices, but Wi-Fi devices are particularly the access points are attached to the wall power. That is the same, OFDM is the same technology that is the underlying communications technology in 4G cell phones. It has tremendous advantages from intersymbol interference and therefore link margin and how many people you can put on a channel in a given space and maintain a certain level of bit error rate performance. But it is very computationally intense. And the work that was going on in the 80s could not be deployed in a cell phone because you couldn't possibly build a handheld device with a small enough battery that would make sense. In fact, it took all the way to the beginning of this decade before it could be introduced into a product. And that was because of the advances in the devices over time in the semiconductor space. So node after node, we got performance improvement, we got power reduced, and we were finally able to implement that concept in a phone, even though computationally it had been known for years and years before that. So I maintain that while we can spend a lot of time in BTUs in the architecture space, we've eventually got to come up with another device or we're kind of stuck. And so, yeah, look at the history of devices, and just past the turn of the 20th century was the vacuum tube amplifier was invented. Middle of that century, Bardeen, Shockley, and Bertin invented the point contact transistor, which became the bipolar transistor implementation shortly thereafter, and then in the 60s came the MOSFET. So kind of every half century or so, a new device comes along, and those two devices are dramatically different between a vacuum tube and a silicon transistor, yet look at their IV curves. Outside of the scale, they're essentially identical, and I argue if you took someone that designed in vacuum tubes and dropped them on the planet right now and put them in front of a workstation, he could design an amplifier because the fundamental device characteristics are not that much different. Yeah, there's a lot of other factors, but basically could do that. So what is that next device that may have similar kinds of IV properties that we can use the existing workforce that's out there that knows how to handle those things and take us for at least another half a century further? So SRC is investing some time in a couple of centers, StarNet and NRI, to try to identify potential candidates for devices, and likely any embodiment will be a hybrid system where you'll have standard CMOS devices along with these specialized devices to do some sort of computational capability. We're benchmarking them, not just as a device, but in a circuit. This is a 32-bit adder, and for reference, there's a couple of green dots there for CMOS. One's a high-performance CMOS device, and one's a low-power CMOS device. And you can see where the devices fall. Nothing in there today stands out as a device of the future, but none of this stuff existed 2 or 3 years ago, and the number of concepts are exploding because of the funding of this and the benchmarking characterization of this. I argue that if you look at over the course of history, what's again differentiated us is power. We went from NMOS designs to CMOS designs, even though there were twice as many transistors, which meant the cost of the product went up simply because we couldn't stand the power. We went more recently from single-core, single-threaded CPUs to multi-core, multi-threaded CPUs. Despite the burden it was going to put on the software community, which it did, simply because of power. We couldn't tolerate the power consumption that you would be going exponentially increasing on a single core compared to linearly increasing on multiple cores. So power is a key parameter here. The lower left corner is where you want to be on this chart, sorry. Energy's on the left-hand axis. So where you want to be is, if you can come up with a device that falls in line with those CMOS devices on the y-axis, so that you get that kind of performance, sorry, on the x-axis, but drop it down on the y-axis to where you have substantially lower power, we will take advantage of a very low power device and live with whatever else we have to give up with for some period of time until we catch up. So to me, the key is, can we develop a device orders of magnitude lower in power? And that's why I spoke about the brain-inspired stuff earlier. Storage, this problem I talked to you about before, we're investing in DNA as a storage mechanism. It's got tremendous density. It's got tremendous lifetime compared to flash. It's slower in read and write times, which is not all that important for storage application. Main problem is it's very, very costly at this point to read and write a DNA memory, yet the rate of change in those in that cost measure for DNA memory has been coming down on a steeper slope. It's much, much steeper slope than Moore's law. So this is an area we're investing in research because we could store that 3 times 10 to the 24th bits with simply 1 kilogram of DNA. Okay, let me talk a little bit about your area, test. This is from the Candy Conference in '86, 30 years ago. The test problem will still be considered NP hard, boring, and unsolved. Well, it's still hard, still unsolved, but it's not boring. Here's some examples, some research that's going on in SRC. The white items tend to address things that are in the new device, new architecture space, and then the yellow ones are security level things that we're doing. For examples, Lee's work here. I didn't pick this out because he invited me here. It's because it's really good work. It looks at test, at probe, class probe, and then final test, and compares that to parts that come back from the field that fail and identify by looking at what data has been collected, outliers, if you will, to then feed back into test programs to extract those devices from either probe or final test before they ever get to the field. This is a tremendous cost reduction. I know this personally. And not only that, as you can imagine, the single best thing you can do to your customer is not piss them off by giving them a bad part. So it says tremendous benefits just simply beyond the pure dollars and cents of the cost itself. Shuli Ozev at ASU, she's done some interesting work in the MEMS space where accelerometers typically are tested by shaking them, but that's very costly and maybe not as repeatable as an electrical stimulus. So she's come up with a way to replace that physical stimulus with an electrical stimulus to model that and be able to implement that in a test program for a MEMS device. And you can see that it had 57% reduction in test cost and an overall 17% product cost reduction. This is particularly interesting given the award that was announced for the best PhD thesis, some work by Chakrabarty at Duke, which also happens to be in the backyard of SRC. So there's another reason why you should be participating in SRC, where he's looked at the 3D test problem. And this is an area that's fairly new, not very well developed as to what are the kinds of defects that you can have, how do I model those defects, how do I partition my testing routine, if you will, between the known good die and then the combined die. And there's a lot of good work that's come out in here, which has resulted in 3 patent applications. And then lastly, some work by Jennifer Dwork at SMU. She's been looking at defining a methodology to capture what normally would escape structural test and be found in a functional test such that it can be placed back into a structural test. And there's been some really good results that they've achieved in that space. So I claim there's more and more excitement to test than there's ever been also. And just looking back at from an industry perspective and maybe this design perspective of what's going on, well, how does that affect the test community? Well, we got these stochastic devices. We're going to have to figure out a way to test probabilistic things as opposed to deterministic things. The architecture explorations will introduce new test problems and challenges for us. Package integration, that's a huge area that where testes have become involved, and maybe test and repair. Test for security, I've cited a couple examples, and then we got these new devices, and what does that mean for tests? So I think that there's plenty of interesting, cool work in the future for the test engineering community. So let me just give you a little bit on SRC, and then I'll close here. The SRC is a nonprofit organization. Our members contribute dues along with government agencies that we work with that will oftentimes find the research areas that we're tackling as being interesting to them, and they'll fund that. So we pool that money together, which creates a huge leverage factor for any one particular member to invest in industry-relevant problems that the industry defines. And I like to say we solve problems where there is no known solution, but if there were one, it would matter to the industry. Those problem statements are captured in a white paper. Solicitations are put out. A couple of rounds of filtering go through, and we select proposals to fund. Output of that is three things: the research results themselves, the IP in the form of patents, and all our members get a non-exclusive royalty-free license and use to that patent, as well as we make sure there's no background or blocking IP in place before we even start the contract with the university that we know of, so that you have a freedom of practice. And then lastly, the students themselves, who come out very well trained, ready to hit the road running on industry-relevant problems that they've been working on in the past. Oftentimes we'll bring them in as interns, start a technology transfer, sometimes as they graduate from the university, speaking from my own Freescale experience there. We have 17 industry members. 5 of the top 10, which are shown there in yellow, are 5 of the top 10 by sales in the industry are SRC members. We work with 3 government agencies: NSF, NIST, and DARPA. We're looking into new areas of DNA-based storage. Talked about that. HCI, we talked about that. Automotive is a big exploding area for sure from a cybersecurity perspective and autonomous vehicles. This JUMP research announcement is what I said that happens tomorrow, which is this research agenda around those 8 vectors I talked about, more or less. Energy efficient computing, we're launching another effort with NSF, and we have a current program that's $7.2 million in size. We'll roughly be doubling that by the start of 18. And then finally, the space of electroceuticals, which is think of pharmaceuticals and replace pharma with electro. So you're replacing a chemical to do drug delivery with an electronic signal to do drug delivery. The main differences being chemicals, a very broad-based application, which can have many side effects, as opposed to electrical. We're targeting going into by cell, providing sensors to determine what's going on and build complex modulation schemes, both amplitude and frequency modulated, to drive the appropriate signal to actually do pinpoint control of disease or injury repair. Exciting new area. So we believe that we're positioned to lead the industry as SRC has for the past 34 years. 16% of all publications relating to the semiconductor industry come out of SRC-sponsored research. We have 3 times more papers have really high citation recognition to them. So if we're looking for members to come join us to help define these research agendas, take advantage of the IP and the students that we create. And in summary, come back to my last 2 points here, that we're starting out, we're in a direction now, the way forward is more unclear and uncertain than it's ever been. There's no silver bullet today in terms of a device or an approach. Many things need to be explored until we can really find our way forward. There's plenty, I think, of opportunity in the market. We just have to figure out the technical solutions to satisfy that market. So it comes down to me, the most exciting time in the history of the semiconductor industry is today, and that the discovery of this way forward is going to be dependent upon us as an industry to collectively double down and invest rather than simply cost control for the future. There's no better way to do that than through SRC, in my opinion.